and there are models that define diffusion, right? So the models, Fick's law of diffusion is one of the fundamental law that we see, where there's flux which is proportional to the concentration gradient, and then diffusion coefficient is the constant which gives you this relation. And it's not fitting on the screen. So D depends on the type of diffusion, concentration, and very importantly temperature. So as in empirical formulas what we use, we take diffusion to be a constant, but diffusion has an Arrhenius relationship. So Arrhenius is where it has dependence on temperature. But generally we take it to be a constant. So which is that in the presence of a gradient, we have some flux occurring at a cross section. And if the impurity concentration is limited, what we see is the profile of the dopant concentration reduces and deepens into the substrate. So in a 1D situation, so this would mean if I have, this is my depth, so my profile would be something like this, and then this will keep on going like this. So if this is the concentration, normally we define it in numbers. Numbers is basically numbers per centimeter cube. So we keep on heating. So what are two steps of diffusion? What do we do first? Pre-deposition, right? So we need to get all the dopants into the substrate, and then what do? We drive them to the depth profile that we want. So in time and space, this is how it looks. So second law defines now it in terms of two dimensions. So where you have a delta x, where there is x1 is the first sort of cross section, and x2 is the second cross section. So there is J1 that enters and J2 that exits, because as it goes, it's also the flux is what's happening to flux as it is traveling from one point to the other, decreasing, and reason why we have negative on the equation, right? So it's J1 is entering and J2 is coming out. So we can define it as change of concentration with respect to time, right? So we know with respect to volume element, now we know with respect to time. So if you set both equations, equate them, what we get is Fick's second law of diffusion. It's a generalized form. So now our concentration is not just dependent on time, or not just only the depth, it's a partial derivative of both x and t. So it depends on the distance and the time it takes for them to go. So diffusivity is not a function of position, so it's independent of position. So we can generalize and take the d out of the relation. So what we are left with is a simplified version of second law of diffusion. So it can be valid only for small concentration, where we have very limited supply of dopants, and that would be less than intrinsic concentration. Now, what is intrinsic concentration? What is the intrinsic concentration of dopant?
Concentration without the pure.
Concentration without the introduction of the deliberate, what you call extrinsic introduction of dopants. And what is the value of those? 10 raised to power 10, right? So that's what we call intrinsic doping or background doping, so which is always there. It's not good enough to make semiconductor into a conductor. They don't provide enough charge carriers, right? But something that's below that, then D would have how the dependence on have impact of the position. But above that, we use just general form for high concentration diffusion, right? Now, as a process engineer, what do I have to know for diffusion? As a process engineer, what do I have to? I have this equipment where we do diffusion. What do I need to know?
Temperature,
Temperature,
time,
time,
and I guess the concentration that you're
concentration of dopant.
right?
Not just concentration,
And the crystal's lattice orientation.
lattice orientation, fraction of dopant, right? Because we use inert gases, and I need to know the behavior of my machine. Right? How do we know behavior of our machine? What do we call that? Checking out the behavior of machine? Metrology.
Calibration.
Metrology. Right? And by metrology, we would calibrate our equipment, right? So what is metrology for diffusion? For oxidation, you have metrology, what we call ellipsometry, or color, right? For diffusion, how do we measure the diffusion result? Conductivity, right? That's the ultimate goal. So the dopants are supposed to change the dopants are supposed to change what? Conductivity, right? So we can measure the conductivity of wafer. How do we measure conductivity?
By measuring resistivity.
By measuring resistivity, yeah. So how do we measure resistivity? By measuring conductivity. You are in front of me and I'm in front of you, but where are we? In front of each other.
But we can, we can do a resistance curve.
Yeah, so it's 4-point probe measurement system. So there's something called SIMS. So we have this metrology tools where we measure the conductivity, right? So we don't just look at each other that we are in front of each other. So we have. So then for intrinsic diffusion we use simplified fixed second law. For extrinsic we use general fixed second law of diffusion. So, but for pre-deposition, the rules are slightly different because what we do is we don't have any boundary condition once we start. So we have only this region, this red region that we do pre-deposition. So for that case, so of course these are just boundaries, no dopant at the start. CS is for the entire cycle, the amount of dopant that's available, and this at infinite distance there is again concentration goes to 0. So this is an error function that defines the concentration of the dopant after this pre-deposition step. So pre-deposition is high concentration, high temperature. The idea is to get the dopant across the boundary from gas to solid silica. Once you get in, then we just drive them in. Right? So this is an error function which is defined by certain integral. So the idea is that as we increase it, the distance and time, we get a certain profile which is not linear. It has exponential dependence on the dopant, right? Which comes from this guy, integral of the exponential. So, but once you do that, we do this for fixed time and our junction depth. So there was this chart last lecture where we had these junction depths. Right? How small is the junction depth in devices, current devices? Do you remember those numbers? There is this plot, I think, in previous lectures where you look at the, let's see.
There were several nanometers, maybe?
Yeah, I think there's tens of nanometers. I think. Let me check. So why that's important? Because our junctions are becoming very shallow. And obvious reason is because the device is being scaled, so channel is too small. We don't want the junction is source and drain. We don't want them to go too deep. We don't want them to be very close to the surface. And that means that our diffusion has to be very well controlled to the close to the surface. So the junction depth is then has to be very small. That's so when I define my source and drain, if I'm here, I have large channel in between. But once the channel becomes small, I cannot go to the same depths. I have to make these guys also small. To color code. So as you bring them closer, their depth has to be reduced as well. We could live with deep source and drain when they were further apart. Once they're coming closer, so now if I have source and drain, I could make these deep pockets while they were apart, but now when they are becoming close to each other, this is channel region, I have to keep them shallow, can't go deep. So this is deep, this is shallow. If you now consider each one in their own space, say this is N-type and then of course the bulk will be P. So this is nothing but how can we model this P and N-type material in contact? It's a diode, right? So if you look at the physics of diodes, what we have is N-type material and P-type material. So in this case, N is heavily doped, right? Because that's making the source. That's conductive. That's supposed to be electrically very, responsive. So if I make this guy, what we call N plus, what is this region at the interface? What do we call this region? Depletion region, space charge region, right? So depletion region is called depletion region because what do you mean by depletion region? Depletion.
No free carriers that are ionized.
So the majority can.
There's a voltage barrier.
There's a voltage barrier.
Carrier cannot cross.
Carriers cannot
Unless
cross.
it provides some bias.
Right. So there's barrier because the carriers are depleted in that region. There are no carriers available. There are no free carriers. Not as many free carriers available as there are away from that interface. Right? And simple reason is if I bring two types of say magnets which are opposite polarity, they would attract each other. Right? So they would neutralize each other. They would try. So here again, if you have P-type excess, N-type excess, they would bind to each other, neutralize each other, so to speak, and you'll have very less free carriers, free charge carriers, free majority charge carriers. Right? In N-type, there was supposed to be N electron were supposed to be majority carriers. P-type, the holes are supposed to be majority carriers. But in that region, they are too few. Right? Now, this is a boundary which extends some distance on both sides. Right? So this was the actual physical interface, but they are extending to some distance on both sides. How deep do they go either side? Depends on how much is that region doped. The higher it is doped, the more it will be in that side, or less will be on that side? Less? More? The higher it is doped, the more that region will extend into this, or not? Why? If I'm heavily doped, I can bully around, right? I can push to the other side. Simple reason is, if I'm heavily doped, I can contribute many more. So the other guy who has very few can neutralize very few of mine. I have many more extra available. So this region extends. So in this case, if I make, this will extend a lot more into that region, because this is just P and this is N++. Because it has many more charge carriers and this has very less. So they would travel much more on that side. So this region has shifts more into the side which is less low. Right? Simple physics. I hope I'm making it out simple. Because if I'm N plus, from next to SP, I have more charge carriers, more. So I'm more strong. I can push the other side of the line and take much more of the region on that side. Now, looking at those devices, when you are bringing them much more close, there is always this phase charge region here. There is always depletion region. Same thing here. Right? On both of them. When we bring them closer, and this is P type and this is N plus, which means that this depletion region is always extending more into substrate, into the bulk. Make sense? From same analogy from there. When you bring them too close, those depletion region will merge. I don't want them. Right? So, but I can't reduce the doping value. What I can do is I can make them physically shallow. I can make them physically to be in a very small region, because then their depth will be small and their width is going to be small as well. And this guy shut down on me. Hopefully it will come. So junction depth becomes an important thing. Diffusion becomes a challenge. Let's see. Okay. So this is from last week. Junction depth parameters. So see, when we are going ahead, it's becoming somewhere 11 to 19 nanometer. This is the diffusion that we want to control. How deep we want to go. We want the source and drain to go deep once we are doing a diffusion. It's becoming very hard to control it through the depth. You've seen this before. This is from last week. Should I call TA again? You haven't seen these slides?
We didn't get to that.
Pardon?
We didn't get to that.
Let's get to
Yeah,
that.
I'm really not sure if you covered.
He
we were
introduced
out
P deposition and driving.
Oh, then probably we can start from there. So this is from, which I thought were posted online. So is that probably what you're supposed to do? So definition and these are numbers. Why do you want to? What do you want to be worried about? Junction depth. Okay, so diffusion. The junction is how deep we want to go. Right? Solubility. Again, there were just 20 slides last week. So solubility is with temperature from in silicon, which element would be soluble at what temperature? Right? So depending on how deep, what concentration do we want to achieve, we'll have to use that temperature in diffusion. So diffusion furnace is not very different from oxidation furnace, right? But in this case, we are, instead of just giving it water vapor or oxygen, we give them these recipes of gases that we want to dope, right? So high dopant concentration is needed for high performance devices, so they can switch on quickly. They can switch on and off quickly. But that was the last slide from last week, so probably that's why maybe rushed through quickly. Okay, so junction depth is the point where the diffusion concentration matches the background domain, C sub. So what we can do is that we have this area under the curve and we can integrate it to get the amount of dopant that we need to introduce. So when you do this maths, what you get is something like this, where your time as it goes up, given unlimited source, right? So here the concentration is of dopant at the interface is continuous. It says junction. Yeah.
So the intersection between the curve and the C sub will give me the junction depth.
That's the background.
The
dopant.
horizontal
Yeah.
axis.
Yeah. So then you'll have to see that. But this is a conceptual curve. It's a conceptual curve. This is what you are maintaining at the surface, and then you get certain junction depth out of that. How deep it goes, right? So then you can calculate how many are there. So once we put what we need inside, then we drive it to the depth. Now, you guys haven't looked at implantation yet, or you have seen implantation already? So implantation gives us that advantage where you implant them directly and the profile is Gaussian. So instead of a distribution which is like this, what we have is an implantation something which is like this. So we can control how deep should be the highest level of dopant concentration. So if I want to do control junction depth and have this in a source or drain instead of an embedded profile, I can do is I can control the beam and have this peak on the surface. So have it something like, where I get something like this. So this is very close to the surface there. We'll get to that. So now in this case, we don't have unlimited supply, but what we have is a delta function at the close to the surface, right, which is the pre-depth. And this is now what we use to drive it. So in this case now, Cx sub 0 is 0 for x above this delta function, right? So now we start from that interface. And now if you solve that equation, we get a Gaussian distribution on that falls off on the other side. And if you keep on doing it for longer period, this is the profile of the dopant. So if you look at the dopant profile, a plot with dopant profile, that should tell you right there if this is a diffusion process or an implantation. Because implantation would have a Gaussian, which would have trailing ends on both sides. But in this case, in case of diffusion, this would be source limited form where the profile will just become flattened with time. So now this again gives us junction depth by solving for x, and this is now this depth is now a function of how much charge carrier were there and what is the background diffusion, right? So those are the two important vectors. And dt is, of course, diffusion coefficient. So what actually happens when those dopants get into a lattice structure? We know lattice is a periodic repetition, and there's there's hardly any defect. Like in ideal condition, lattice shouldn't have any defect, because if you have defects, that would cause the mobility to degrade, and we don't want that. We want the highest mobility that we get. Why would a crystal defect cause? So defect can be if there is an atom missing, can be some incorporation of some atoms which don't belong there. What would they do to the mobility? Why would mobility reduce? So you have to think not in terms of conductors, because conductors, we have plenty of charge carriers that just zip through, right? In terms of silicon, in terms of semiconductor materials, you have to think in terms of crystalline structure, and there are these atoms which are rigidly spaced at specified position. So something that needs to pass through have to strike them, right? So collisions are what cause the degradation of mobility, or this defects which may suck those charges in. So defects will be something where there is need for a charge to come in and fill up, satisfy the 4 bonds around it. So those will be electrical sinks. They would hinder the flow of charge. So that reduces mobility. So in case of diffusion, what we do is we get them to fill up vacancies. They would either interstitial impurity, they would self-interstitial, they would find their own place, they would substitute an atom, or they would just disturb everything and get in there. So different types of defects that can come from doping incorporation, and they have their own contribution to the overall mobility. So these are definitions where at different places they're called in a different position. How do we get rid of these defects? How do we get rid of these defects? Let
Heat it up and
heat it up, let it find its place, give it enough energy so they can find their energy minimum and settle down. So it can be during the silicon formation and implantation or oxidation. So all these can happen because of that. But so for different diffusants, the mechanism is different for them to become part of the lattice. Can be interstitial or can be vacancy. So depending on those, we define vacancy assisted mechanism or interstitial assisted mechanism. So in vacancy assisted, they will find an empty space and just fill up the space. And interstitial, it has to kick out something and find its place over there. So for different ones, there is different figure of merit, how many of each would be vacancy assisted or interstitial diffusions. Now, we haven't looked at, we saw that there's diffusion solubility which depends on temperature, but the diffusion coefficient, what we consider to be constant, also depends on temperature. So when temperature changes, our activation energies change. So what is Arrhenius equation? Have you guys ever seen Arrhenius equation, Arrhenius relation? What is an Arrhenius equation or Arrhenius dependence? It's a what you call a standard relation. It provides a dependence on temperature. Provides an exponential dependence on temperature. So generally, you see the Arrhenius plots which have temperature into 1 over T times 1000. They give you a linear plot. So that shows a dependence on temperature when it changes. So essentially, we take D to be constant, but D or which is part of, which is basically defines activation energy that is different for different domains. Right? So this QA is what we call activation energy. So those show us the dependence on temperature.
What's A sub O in that equation?
A sub?
A sub O. dA equals D.
Yeah, so that's diffusion coefficient or any parameter at what we are interested in and at base temperature.
I see.
Right? So that's a we call base case value. And then at different temperatures, that is a multiple of that exponential dependence of temperature. So Arrhenius relation is not just for diffusion. For anything that has dependence on temperature, it can be found to be an Arrhenius dependence. So there are some diffusers which are very fast, but that means is if devices are exposed to them, they can get incorporated into the silicon substrate. They can get trapped there. Now what that does is that basically electrically we cannot depend on that device. The device will behave erratically. Erratically in the sense it will not be controlled. Right? So if these, and mostly these are metals, if they get, if our wafer gets exposed to these, they will get incorporated into those defects and cause the electrical leakage and anomalous behavior of the devices. So what we do is we have to be very, very controlled once we expose our wafers to these these metals. After that, we don't expose the wafer to high temperature because they can leach through and get into the what we call structure of the crystal.
What's AU, AUI, and AUS? Are they?
I think they're gold different diffusion coefficient. I don't know exactly why I sub S sub, but these are values for gold. And this is a fairly low temperature, right? So the oxidation starts from about this temperature. Right? So if I have metal on there, I would just get these incorporated into the devices. But one would say metal we can understand. What about these gases? So we do use these gases also to increase or reduce some effects. So we'll see, we may use them to our advantage to let them diffuse through the silicon substrate. So that changes the front end of line and back end of that, differentiates those two processes, front end of line and back end of line. So arsenic, what kind of contribution is arsenic? What type of dopant arsenic is? N-type. Right? It is slow diffuser and gives an abrupt profile, which means that you need a lot more temperature to drive it in, and then once you get it, it doesn't travel too fast beyond that marking. So it has very abrupt profile. So this is depth, and this is the concentration. So we start with 10 raised to 21, right? So, and it falls off abruptly. So it may be something we want to do for shallow junctions, right? So its total, what we incorporate, can be much higher than what actually contributes to the conductivity, to the mobility. And would that be good or bad? Okay, so we see that the plus is that it gives a sharp profile, right? Which is good. We need this source or drains to have very sharp profile. We don't want them to be extending beyond what we want them to do. But then, if you have much more of it incorporated than what actually contributes to the conductivity, what's wrong with that?
They can diffuse later elsewhere and make unwanted contacts.
They can diffuse, right? What else? You have to get that again. I'm repeating myself. You have to remember the transport of carriers and crystalline structure is different than conductors. So if you have many more of people crowded in a room, is it easy for me to pass through? Or is it easy for me to pass through if there are less people in the room? And many of those people are doing nothing, just sitting around. Right? They're not contributing. So what do we want? So much more crowded dopants which don't necessarily contribute actively is good or bad? How?
It's taking the space. Right?
It's degrading. It will degrade mobility. It will degrade the travel of charge carriers because there will be much more crowded. What happens in the crowd? You bump around much more
Energy.
collisions. There will be many more collisions. So collisions would retard the travel of charge carriers. So, and they are not just simple atoms lying around, they will form clusters, even worse. Right? And it's good if everybody's standing on his own, I can still sit through. Still like 5 people holding hands, and then it's hard to maybe get through. So, they form precipitate and dissolve. So, a good plus, they have very rapid profile, but the bad is many more are not active in there. Boron is a p-type diffuser. TED is, we'll see TED next few slides, transient enhanced diffusion. So we have this very thin pre-depth, which is, it helps in diffusion. So it requires rapid thermal yield to control the diffusion. So if you see its depth relatively, it is wide. So it's not an abrupt dopant. It will take some distance before it gets to the background concentration.
That's TED.
TED will see it's transient enhanced diffusion. It's here. So there's many silicon sites created on very close to the surface. So that causes a transient enhancement. So once we do introduce them at the start, this is introduction by implantation, not by pre-tap. So that results into many more sites at the surface. And once you do that, it's very easy to control the profile. Right? So now this is a combination of ion implantation and driven, not pre-dep and driven. Right? So it works well with TED. So this shows that if you don't do any annealing after implantation, you have very nice profile very close to the surface. But once we do the annealing for 7 seconds, so this results into the spreading into the substrate. But that's called transient enhanced diffusion. The difference is we are not doing pre-dep, we are doing implantation and driven. Right? Phosphor. It's also fast, but it's used in place of N-type. It has complex characteristics, and you can see that. goes like this, falls down, then goes. So this is probably the region that is of our interest, but this region is something that is just causing a deep profile for the dope area. Right? So this is again depth. So if I want to get rid of this part, then the only way is if we reduce the doping concentration. So that's again opposite to what we want. We want highly doped area.
Is arsenic smaller in size than silicon atom?
I think so. Yeah. I'm not sure about the sizes.
So the doping profile, does it relate to the size of the?
It would, yeah, it would depend on the size of the dopant. But I'm not sure relative sizes of these dopants. They would be, yeah. They are, but I'm not sure if you start comparing. I would have no way of telling which one is what. But yeah, they are supposed to be small. Right, so it has a complex characteristic which gives you three distinct profiles, and it has what you call plateau, kink, and tail. Right. So this is plateau, that's kink, and then there's tail. So it has both of the mechanisms. At high concentration shows vacancy profile, and a low concentration shows kick out mechanism. These are two mechanisms which we saw before. Right? We don't do only diffusion in silicon, what we call single crystalline silicon. We do doping in other materials. Polysilicon is one example which we use to replace what? Where do we use polysilicon?
With conductors.
To replace conductors, right? So gate stack is made of polysilicon, heavily doped polysilicon. So it's now polysilicon is something that is grown from grains. So there's small grains which nucleate and then they spread and they join each other to form a film. So now they have many more boundaries in their what do you call it? In their texture. So they would be boundaries of many boundaries of, if you look at polysilicon, so and this is like each grain has localized crystalline structure, right? So these boundaries are now what get many more locations for the dopant incorporation, right? That's 100 times greater than bulk silicon diffusion, which makes it heavily doped. Right? So then one can ask, okay, before this we could have said, which I was wondering, but nobody asked that, okay, if we dope silicon too high, mobility goes down. What about polysilicon? It's not a bulk mobility now that matters, because now these are different grains. There are many more boundaries which can have many more charge carriers and interference. Now they don't even have to now, charge carriers don't have to pass through the bulk. And they travel on the surface. So grain size structure orientation is what we defined during our poly deposition. Right? Poly is deposited by LPCVD. And we'll see LPCVD later on. But that can cause a problem that if you have heavily doped poly, then again our temperature budget reduces. We cannot elevate them at high temperature, the devices, because they can subsequently dissolve and get into the substrate. And they are what you call poly depleted. If you do too high of dopant concentration, then that becomes a problem, because the gate, this would reduce the charge transfer through poly. That would essentially contribute to the virtual increase in oxide thickness, right? So instead of becoming a conductor, then it start becoming impeding the charge transfer. So the heavily doped to avoid poly depletion. So that effect that it doesn't add to the resistance of the gate. Diffusion through silicon dioxide occurs, but the rate is different. So it's used for patterning, so it's less than 1% for all dopants. But at very high concentration, that can occur, and it can result into glassy oxide, which can move the silicon through silicon dioxide very fast at high temperature. So, as a process engineer, I have to know what mask I can use, because my desired doping profile, doping condition will tell me if I can use silicon dioxide or doing silicon nitride. So in both cases, that will be different. Just like etching, in etching we saw that concept that the selectivity defined how thick of the mask material we need. So once we get done with the actual etch, we are still left with some of that mask material, right? In this case, we are not etching something away, but we need to know how much of the dopant can pass through, right? Through that mask material. Because I don't want, so if this is my mask and this is my desired junction, I don't want them to go through this part. So if it's high temperature, then I expect something to go through, then I will define how thick should this be, or what material should be. So material of the masking material and the thickness of masking material will define how can I reduce passage of dopants from the masking material, right? Because I just want them to go in this region.
So where does this glassy oxide forms?
At high concentrations of group 3 and 5.
Do we ever
That species passes through.
Does it come over the oxide layer?
No. It's not a film. It's P2O3 is what forms and seeps through. So that molecule can. So it's not a film that's growing. Okay. It's a material P2O3 which is.
P2O3 is diffusing.
Yes, diffusing through silicon dioxide. So that oxide of phosphorus will diffuse through oxide. Right? So then it will be our choice to use silicon dioxide or silicon nitride. Right?
So do we ever want to dope silicon dioxide? Or is this something we just have to know about and avoid?
I think that there is something that we want to do it, because that changes the type, changes the physical properties of silicon dioxide.
I see.
Yeah, I think there's one process. There's one dependence on changing properties of silicon dioxide. How does that happen? It is somewhere. So, E-field enhancement. Now, once we do this diffusion, now there is an electric field at the interface, right? What we call built-in voltage, right? So, it helps diffusion. It enhances diffusion. So that causes dopants to drift in that localized electron E field, right? What is drift?
After a
Bias.
Drugs. It's a drug. There are so many people talking. So, what is drift?
That is due to bias
Due to bias, voltage,
velocity occurs. Drift velocity occurs.
drift, velocity occurs due to voltage bias. Okay, so it's nice to have the same word in the definition that you want to define. So drift occurs because there is drift occurring.
No.
Okay, how do you define drift? What's the difference between diffusion and drift?
Diffusion is related with concentration, like
Concentration.
high concentration.
So both are movement of charge.
Yeah.
One is
Carriers.
against an applied field, the other is not.
Yeah.
Right? So drift is what happens when you apply a field. when you bias, when you put some batteries around, right? So then charge flows. So drift is when movement of charge occurs in a field. Right? Field, when you have positive bias, negative bias, they travel towards opposite electrodes. Right? Negative charges go to positive, positive. So E field enhancement is you have the built-in electric field, and that would cause dopants to not just travel under the concentration gradient, but also under the bias, also under the electric field, which is helpful, right? So now they can travel further. Now their travel is not just a factor of energy that we are providing with temperature and the bias, not the bias, and the potential of concentration gradient. Now we have electrical potential also involved. So that enhances the dopants to do better. So we can now make them go deeper. Does that make sense?
So how big a field do we apply?
We don't apply. That's inbuilt. So once read. There is a built-in electric field which helps. So dopants are ionized, but there is a built-in electric field that helps us.
I see. So this is something that we have to consider in our modeling of diffusion, not something we necessarily cause.
Yeah, we don't model diffusion, which is, we know this all, but so that helps it. So that field on a substrate helps us putting diffusions even deeper, on top of just the concentration gradient. Right? So now the thing to probably point out here, concentration gradient also provides a potential, right? There's a potential energy involved in concentration gradient as well, which we discount. We just say, okay, this is happening because of the difference in concentration, but can't produce work without converting it from one form to the other. So if there's potential energy between. So this is electrical energy now, which is present, which causes the enhancement of the diffusant to drift in top of diffusion. So emitter push. So emitter is part of a bipolar junction transistor. We have been looking at source and drains, which are MOSFETs, but in DJT there's a part called emitter. So it was seen that if you have emitter, then that goes further away from its intended region. So it happens by phosphorus vacancy pair. So it's called emitter push. That results into further deep part of the under the emitter. So this was an issue which has been taken care of by using arsenic for emitter push, for emitter dopants. Now, so we see, okay, junction depths have to be brought, made smaller, right? But then when they are becoming closer, there is lateral diffusion also, which is causing the space charge region or depletion region of source and drain to overlap. Right? When they overlap, it means we are already making the connection between source and drain, already causing them to short, which means essentially we are losing control over the gate. Does it make sense? You just said 250. Let me draw it. So, in one case, this was our source and drain. Now we bring them, we have brought them together. We have made them shallow also. Right. So there is this space charge region, what we call depletion region. Right. Thinking of it like a diode. So this was N type and this is P type. So in both cases, we had this guy. So as a region where there are not many majority carriers well done. There will be some which will be extending in this side also, but this is way higher, so we ignore that. We say, okay, most of the depression region is towards B side. Right? Now, when these come closer, the depletion regions are almost overlapping. For transistor to work, we had to have this part which we want to control. So it's conceptually this part which we want to control with a gate electrode. Now, when they are overlapped, doesn't matter whatever voltage I apply because they're already shorted. A very crude form what I'm drawing here of what is called short channel effects.
So
There's much more to it.
we have to maintain a certain amount of length for my gate.
Yeah. So what we actually end up doing is we don't make them like this. What we do is we make them something. So I'm keeping the gate. So this is where I will come back again. But what we do is we make them probably deeper, a little away. Then what we have is we call them protrusions. There's a specific word for them. So we have this even shallow doping areas for source and drain. So this is what causes this region to be very small. What you call the space charge region or the diffusion. The depletion region is now thinner because the so these are small protrusion type which come under the gate. Right? So that's compounded with the effects what we call lateral diffusion. Right? So this happens, it's 75 to 85% of the vertical diffusion. And simple reason is because diffusion occurs in all directions. Right? So if I'm exposing a square part at the top and I've done pre-dep and now they're going to go everywhere. Not just X, they can go into Y-axis as well, right? And Z, right? So Y and Z and X. So this is the concept that we want them to stay hypertate, but in the newer device structure, what we have is we have very, very thin junctions, and then we have source and drain behind them. There's a specific name for that. I'm forgetting what's the name. What do we call these shallow parts? Right? So that can happen due to the stress of the mask itself. No way to measure, but what we can do is we can measure from the CMOS behavior. Why would there be stress from the mask level? It says impacted by stress effect of mass level.
Is it the thermal expansion?
Thermal expansion,
Mass,
right? And
mass versus substrate.
right, and yes,
So that's going to cause some stress or strain, or maybe lack of, going to cause the mass to come unglued.
unglued mass, unglued.
Whatever the
Suppose
term
you have
is.
silicon dioxide, which is you have grown out of silicon now. What about that? So there is stress, which is of course thermal expansion coefficient would be different for two different materials. And then one material is pure cylindrical crystalline structures. The other one is partially crystalline, right? So silicon dioxide still, depending on how do we get it there, has what do you call? It was those tetrahedrals and they were joined by with each other. What do we call them? Hydrogen. What were those? So they were those tetrahedrals of silicon dioxide, right? They were making chains.
Yeah, bridging, right?
Bridging. So depending on, so there's bridging there. So this silicon dioxide still has some structure, which has its own strain. So the strain of silicon and silicon dioxide would be different. So that's a mismatch. Don't call it lattice mismatch because of course one is lattice, the other one is not. But there's a strain between two different ones, and thermal coefficient is different. So that can cause. That's also contributor to the lateral diffusion. Right?
So I have a question. So why we are using the term the mask? So that your saturation under a mask. So what do you mean the mask?
So when I'm doing my diffusion, before I do, I have to define a region of where I'm going to do this diffusion. Right? So I have, first I have this silicon dioxide, for example, and then I open this window through which I'm going to do diffusion. My end goal is to have diffusion something here, right? But this is ideally what I want. But what I end up getting is something which is maybe same depth, but something which is like this.
So what is the difference between lateral diffusion and emitter push? The previous term.
Yeah. So emitter was, you make emitter, and after you are done, you see that, yeah, it's an idea that it's pushing, but it's pushing the whole device around it. So this is what causes emitter push, essentially. That is it. Right. So what we end up is we have 75 to 85% going on the side of under the mask. How can we get rid of that? How can we not have this lateral push? Use ion implantation. Right? And implantation is exactly where we want to go, right? And up to what depth you want it to go. So essentially, we do ion implantation in all the devices. Right. So, in questions
So
on
is
diffusion.
ion implantation a more expensive method? Because you have to aim the ions the slower method, or is it?
Cost?
Yes.
I don't know, but as it seems, ion implantation seems to be cheaper because that process is fast. You don't have to heat up the furnace to that high temperature.
I see. So
Just-
it's not
just
like
combine-
an ion beam lithography.
It's ion beam. It's just like that. You are impinging ions on a surface.
But you're not necessarily having to control it as finely, right?
Yeah, you have a mass material which is covering where you don't want it to go.
Okay, so you don't have to steer the ion beam as well.
You have to.
You have.
Yeah, we'll see ion beam. Probably should have been ion implantation here. I
So
don't know
which
why.
method is being used frequently nowadays?
Ion implantation, because the junction depth is too thin, and short channel effects are becoming very, very enhanced, they are overtaking. So we don't want lateral diffusion worker.
Because my device are being scaled down nowadays, so junction length might be shorter. So that's why ion implantation is being
Scale
used.
down, which means my junction depth has to be shallow,
Shallow.
and then because source and drain are coming too close, I can't afford lateral diffusion.
Yeah.
Right. So
Yes.
there are many,
That's the
many
reason.
reasons for, and cost. It's quick, rapid. Ion implantation is quick. Just implant, bombard them, you activate them, you're ready to go.
Please go to slide number 5. What's the difference in the mathematical expression of simplified fixed line and general fixed line? I think it was in page number 5.
Yeah, have to go one slide at a time. So this one is where you are treating diffusion to be a partial derivative of x, because you have, okay, so at higher dopant concentration your D becomes constant, you can bring it out. So that's the difference between these two relations. So if D is independent of position, D can take it out. So D
Is
is,
it really dependent on position?
yeah, if D is, okay, so if the dopant concentration is too small, then it becomes dependent on X, because the temperature gradient has dependence on temperature as well. So temperature gradient would be different. But if you have unlimited supply and you are doing high dopant concentration, then it's independent of distance. But generally we use only extrinsic formula. We use generalized formula. Right? Let me see, I think it should be implantation here then. Probably seed required. Maybe we'll start implantation next time. Yeah, let's, from what I see here, we have lithography planned here after this. So diffusion is not just what we want to do with silicon. We are worried about diffusion through mass material. We want to do diffusion in polysilicon, in the material that comes after we make the device. And it restricts the temperature that we can use afterward. Because once we use polysilicon for vias and interconnects, then we cover it with dielectrics, with insulators, that restricts what temperature we can use afterwards, because they can leach into those insulating materials. That's for the use of polysilicon as metal, as what you call low dielectric materials. But once we have
The same is true for ion implementations.
for polysilicon, what we do is in situ deposition. So once we are depositing polysilicon, we have dopants that go inside the furnace. So we dope polysilicon while it is being deposited.
Not only diffusion, ion implantation also put a restriction to the temperature.
Yeah. So but diffusion is what we do for polysilicon, right? So diffusion is ion implantation, which doesn't make sense for polysilicon, because we can do that while we are depositing it over the whole substrate. Yeah. In ion implantation, ultimately once you get dopants to their profile, they are treated the same way after that. Because in case of diffusion, you have pre-dep, which gives you that zeta or that delta function on the substrate, and after that we do dry wet. In implantation also, we put them to we put that delta function, instead of right on the surface, we put it at certain depth. And then we do dry wet. So essentially after that it's the same. But the difference is that in ion implantation we can have that peak of the distribution at some time, right? Which we don't necessarily need if we are doing a source and drain deposition, a source and drain implantation, because we want that peak to be on the surface. So then it behaves the same way like diffusion. The difference is only how did we get them into the substrate. In one case, we have to heat it up high temperature, right, and then do it. In another case, we can do it essentially at room temperature, just bombard ions. Everything else stays the same. Your mass material is the same. Your thickness would be different, because in implantation now they can travel through certain thickness. So unlike diffusion, where it can withstand 99% of the dopants out because they're just diffusing, in ion implantation they can penetrate through. But the good thing about ion implantation, it can be done at relatively low temperature. So you can use even photoresist as a mask in ion implantation, which you cannot do for diffusion. Why is that? High temperature. That will just burn away. That we call burning away as ashing. Becomes ash.
So you said ion implantation is faster than diffusion, but in ion implantation you need to do annealing, right? So doesn't that?
You have to do what you call annealing in diffusion as well. You have to activate. You have to do activation run in diffusion as well.
So what you're comparing is only the time of the dopants entering.
Not just time it takes to get the dopant into the substrate, their profile, the initial profile as well. Right? So, so profile not only how deep, but how well confined in space it is. How well confined in the what if you call it X and Y. X, Y is in 3 dimensions because it will be very well confined into one thin region. And then you can anneal it to activate and drive them to whatever depth you want. Right? The question is, when we put them in 3-dimensional substrate, how do I know the profile of dopants in the substrate? How do I know where are they gone? Okay, now conceptually we see the equation and everything. I can see oxide color. How do I know the dopant concentration? Good question.
Is there a way to stain that?
Stain? They come out of biology. Yeah, come out of biology. Think about it. So if I can give you a hint. If I look at, if I somehow cut my wafer like this, and I have different doping concentrations, right? Can I measure the resistance at different levels? How can I do that?
You can measure the sheet resistance.
Just have a probe and make it travel downwards. It's essentially how it is done, right? But those probes are very, very, very fine in the tip, because now they have to measure how does sheet resistance change, right? And that can relate to our profile. How can I measure vertical or lateral diffusion that has occurred? How can I measure lateral diffusion? Now I don't have to cut it, slant it. I can just put the probe on the surface. I can remove that oxide and now measure. I know where my oxide was supposed to be. And now I can measure and see how does the profile change. Right? At high concentration, it will be less resistive. Right? And of course, that will give me a surface profile of the dopant concentration and vertical profile. That's exactly how it is done. I'm forgetting what is that process called. I'll find out. Right? Question?
I have a question on cleaning actually.
Cleaning? All right.
When we do RCA clean, why do we need to heat the solution before we?
Interesting question. This is to speed up the reaction. Other way would would be to use more sulfuric acid to make it more exothermic.
Not only sulfuric. Okay, piranha is it's hot as is. Like once you mix it, it's hot. But what about the the other one?
So just to use less of acid, we heat it externally. But ideally, if you use more acid, it will be more exothermic. You probably don't have to heat it.
Even with hydrogen peroxide and the second step of the RCA clean,
Right.
ammonium hydroxide and.
Yeah, so we are just making the reaction more vigorous. So it can do it by itself if you plan to put a lot more of chemical, then you lose chemical there. So nuclear energy is a lot cheaper than chemicals nowadays. Right? So essentially there are different schools of thought. Some just do prana, they don't do any heating. Right? So, but the end goal is the same. You want that reaction to be vigorous, that it cleans away everything that's there on the surface. Right?